All right. Hello, welcome, everyone. Thanks for coming to this talk. Before we start, just an FYI, this is the same talk I gave actually yesterday at NDC Oslo. I have plenty of more stories than just from those in this talk, but I didn't feel brave enough to switch them, from day to day. So you're going to get exactly the same version as from NDC Oslo. So people viewing the recordings, there's not going to be nothing new. Maybe in future versions. So you know me, hopefully, know about me. I'm the only context that is important or interesting. Why I talk about war stories, I'm on the .NET team for 14 years, roughly, a few months. And along the way, I started as an IC, as a individual contributor, as a developer, grew up to management position eventually, and I get a couple of some interesting investigation things which are fun, and hopefully I can share them with you, and you can either learn or you can at least start appreciate the grunt work that we have to do a little bit in the lower layers, and why sometimes we might say no, and it's not just that we feel like we want to say no, but it has good reasons. So agenda, what I'm going to be talking about. So I'm going to tell stories, mostly about investigations on .NET team. They are not only from me, some of them are actually from my colleagues, so I'm not that cool to do all that stuff, and there's going to be lessons learned on the way. What's not on the agenda, you will not see any source code, no debugger, and you don't need even like super deep knowledge about .NET. I'm going to educate you on some of the stuff. You can ignore that, it's not super important. So if you expected some kind of debugging and tooling, like Jonathan just showed in the last talk, you might want to stand up and go to Ben's Ben's talk right now. I'm not going to be offended. Don't worry about it. Alrighty. So I'm going to start with my first serious investigation. So it was actually in 2006, January. So it's an old story, but it was basically my first difficult investigation, and I was like 3 months on the job in Microsoft, so it was kind of fun. And what happened is that there was some build lab for a Windows component. Honestly, I don't remember which one it was. And they had a build break once per week. And the build break back then was just like access violation dialog, so they had to log in on the machine, click the OK button because there was nothing that killing that stuff. So it was kind of productivity bummer for their organization. I don't even know how large it was. They interestingly, just recently before hitting this, they updated their tool set, which means the set of tools that they run to build their product to 2.0 RTM, probably from some beta. And so this, when they look at it oh, we updated, all the compilers or the runtime, that must be it. That's their fault. Like, how else, right? If you change something, it breaks. That's the first thing to to blame, actually. Interestingly, they were capable to get repro out of that. And even before the repro, it was actually an interesting story that first they blamed MS Build because that was the first thing on the line. So MS Build team look at that this is how you collect the command line, found out that it's C#, so they throw it at C#, look at the call stack and things, and then threw it at us in runtime, and actually specifically metadata. We're going to get to that. They had very great thing, and that they had a repro. They basically ran the build in a loop, and once in roughly 50 times it failed, and they ran it overnight, which was crazy number, 77,000, 250 hits roughly. So we had pretty decent repro. That's called a repro, even though if it's not 100%. But if you have something that can reproduce in a certain time, certain period, that's a good start. So that was cool, and from that, eventually they got call stack. They have to kind of set up actually through Watson. You had to kind of enable for these buckets to collect heap dumps, and that collected the heap dumps because I don't know why nobody told them to kind of set up the registry keys. I didn't, 3 months in the job. I didn't know what WinDBG is almost. And we got call stack, and we could look at that. But before we get to the call stack, I would like to kind of show a couple of quotes from the email that I found out, which was pretty funny. So the first one was, saying that, the actual call crash is occurring in the boilerplate stack checking code. It was somewhere in metadata. Now, if I was more experienced, or if there would be more experienced people, or if it would be these days, as soon as you see kind of stack and corruption or stack checking, that's the warning, there's a security issue. Nobody said that, so we played it cool. Well, kind of. And the other thing was actually funny that, I told the person when I am immediately like, hey, I just inherited the code. I inherited the code and I started Microsoft, so I'm not quite sure if I'm gonna be able to figure it out right away. Eventually I was. So here's the call stack that we got. That's the only call stack you're gonna see today. As you can see, it starts with actually C# at the very bottom. This is from the times before Roslyn, so it's actually native compiler. And I kind of cut out parts of the call stack that are not interesting. If you notice that higher up on the call stack is actually when it comes to CLR, that's the MS Core Works DLL, and the regmeta is the metadata engine, which I happen to own, and there's some kind of destructor of some read-write lock or lock. Lock, and something is happening over there. And so the question was like, who corrupts this memory? Like, how come that this thing is corrupted? This is weird, right? So that was the first question we asked, and the first obvious answer that comes to developers' mind, like, oh, GC. GC is the thing that kind of goes and pokes at things and changes things and rewrites things, and then no, wait a sec. This is pre-Roslyn date, remember? There's no managed code running in this. This is pure native, right? The C# compiler is pure native. So okay, that was a mistake. So what else could we do? So I digged into that and found out that between the caller and callee, there was actually changed value, and even more, there was actually single bit that was changed. So when you see single bit and you talk with your friends, or people on the team, they tell you like, and ask, who corrupts it? Like, hey, there's this GC card table, and GC kind of flips the bits, and maybe it got confused and things, and then you remember like, of course that's not GC, like because GC doesn't run in this process. We already kind of established that. Anyway, so you go dig deeper and ask like, could it be hardware, like, bit flipped and things? And it's like, nah, how could hardware always fail on the same thing? But maybe. So you ask the team, hey, by a chance, does it reproduce only on one machine? Guess what was the answer? How did you know? Okay, now we're getting somewhere. So, there was one sign of, mysterious bit flipped. If it happens always on the same machine, and the only machine, the first thing is, but you start suspecting that. But then you kind of bug yourself, like, why is it always the same call stack? That doesn't make sense, right? If the hardware is buggy, you don't know if it's the processor, maybe the memory that, here and there, like flips bit. Why would it be the same call stack all the time? That just doesn't make sense. It's a good question. There's no answer, maybe some magic, or maybe because it's, the compilation process is usually kind of deterministic, it ends up with similar kind of code paths, and you're just lucky to stumble upon the same physical memory. I'm not that much into OS, kernel, how it does mapping, but maybe we were just really magically kind of lucky. So what was the lesson that I learned from this? Well, not only from this, was actually that debugging hardware errors is extremely costly. I think I burned like at least 3 full days on this, and I pulled in a couple of friends because you look at it like, does it make sense? By the way, I learned with this investigation, I knew x86 assembly quite well by then, but this kind of forced me into like, hey, this is the parameters are on the minus from the stack SP, right? The locals are higher up. So if you ever need to learn x86, I recommend issue like this. You're gonna know it left and right afterwards. And the kind of key outcome for me from that was that often, or almost always, actually, whenever there's some suspicious issue from customer or on GitHub anywhere, you're gonna see this question from me: does it happen on more than one machine? And if it happens only on one, I'm not talking to you, because it's not worth it, right? The cost, the investment is so large. Now, obviously, if it's large customer, if it's like super duper large machine that you don't have 2 of them, like we would look look probably a little bit farther, but practically that doesn't happen. So that was the story. Now, I would love to say that, yeah, after this one thing, I was so smart that I came up with this and I kind of lived up to that. Obviously not. But actually, a couple of years later, I ran into similar case where, again, after a week, we debugged something to hardware error, only one machine. And that's where, since then, honestly, that's my mantra. Always, when I see something suspicious, first question you're gonna hear on me on GitHub is, does it happen on more than one machine? People are usually like, why are you asking that? This is why. Anyway, it was cool story, 3 months in, and you go debug, hardware issue. So now we were around metadata, kinda. I would like to tell one more story, which is recent actually. It's 1 year old, which is recent for me. First, I have to give you a little bit background on metadata, and specifically on metadata format. So metadata is basically a database. And actually, first of all, what's metadata? In your executable or DLL, there are two parts. There's the IL, that's the kind of intermediate language, so that's kind of IL instructions. The IL, that's kind of the code, which is not yet the machine code, but it's the intermediate language. And there's as well metadata describing like which types you have, who inherits from what, how is it named, which methods you have, and the methods tell you, oh, and in this offset, this is where my code is. This is where my code lives. So that's metadata, and it's basically a database, right? It was designed by people who did databases, by the way. So that's why likely. And it has rows, it has columns, it has tables. So example is type definition, as in like defined types. You have a table, and it has different, each row is basically entry of one type that you have in your assembly, and each column is, represents something. So one is flags, other one is, for example, type name space, what you extend, which other type, and method list. And there's a couple of more that I left out. This is example. Now, what's interesting is that, for example, the strings, the type name and namespace are not directly in that table because that would be variable size. What it has is actually index into the so-called string heap. And the indexes are stored smart because back then, which is when it was designed 20 years ago or something like that, memory really matters, or size really matters. These days it matters again because of mobile. So if you have less than 64K strings or 64K size of string heap, you could actually use 2-byte index into that. So we would use just 2 bytes. If it was larger, you would use 4 bytes. And the same for the tables. Typically, the tables are, if you have hello world, everything is super small. So, if you reference another type, you can use only 2 bytes to encode that, or sometimes you have to use 4 bytes if you have more than 64K. So kind of simple thing. That's what's going to be interesting. And I'm going to explain what the method list is. Method list is basically index into the method def table, and it's smart. It basically says this is where my methods start. And if you want to find where they end, you have to look at the next type in the table and look at its own things first start, and the 1 minus 1, that's the last one, right? So it's basically this range from the previous one, from the next one, and you. So in this example, the type foo has actually only one method, and it's method number 10. The type bar has method number 11 and maybe more because we don't see the rest in this table. So that's background example. Now you can start poking at that. What happens if the type def, your type has no methods? Because there are types that have only properties. Well, actually, properties define methods. That's a bad example. Apologize. Maybe they have only fields and that stuff. It's rare, but it happens. If it has no methods, then you would see, let's say foo has no methods, it means that the next one, the bar, would be method #10 as well. Which means you would say hey, I start at 10, but I as well end at 10, or not at, but before 10, which means I have zero method list. Pretty simple. What happens, so it's basically, it's about last type def. I see, I can't read my slides even, I apologize. So if it's the last type def, then, the last type actually in the table has no methods. You cannot index just the last type, but you have to index the next one, kind of the missing one. So the +1. And what happens if you have exactly 64K minus 1 methods? If you paid attention, you realize that we have a problem over here. The problem is that, if it happens that the last type has no methods, you have only 2 bytes to represent the method index, and the method index is basically 64K without the -1, you just overflowed. What do you do about that? Well, what do you do? Is that a problem? This is just like simple proof that actually it is a problem in the specification itself. If you look at the CLI ECMA spec, I don't have to read it exactly. It basically, like, these are the parts that basically tell you, like, oh yeah, if you have what is it? If you have like less than, and watch out, like not less than or equal, less than 2 to 16 power rows, then you have to use 2 bytes, otherwise you use 4 bytes. So it's exactly prescriptive how the, if you use 2 or 4 bytes for indexes for each table, for each string heap. In the type definition, type def, it actually tells you that, exactly that, hey, the +1 is something allowed, and you should be able to encode that. When you look at those two things, they just don't work well with each other. And how do you fix that? Actually, the key thing that I forgot to mention, that was really a year ago, we really got this report. It was actually WinRT team doing some cool WinMD files, and they came with this weird error from C# compiler. And Michal, actually, who was on that, tracked it down to basically this, like, yeah, we just hit a spec bug. What do you do with that? How do you fix it? The truth is that, as Michal nicely put it, if you hit a bug once in 17 years, and it has been 17 years since this was introduced, maybe even more, maybe it's okay to not fix it. Maybe let's wait for the next one. Obviously we can try to help the customer or this case, and we try to kind of compensate with that. And you could do things, and we consider things like, for example, you could start rearranging the order of the types or methods and that stuff, because it's not only for methods. But it's kind of nasty, if you compile and like if you compile once, you have this order of methods for reflection, you compile again, you have another order. Again, most developers don't care, but certain tools or certain things are kind of, sensitive to that. People don't like that. Other thing is we consider it like, hey, what if we emit fake type at the end, if we detect this situation, like one more type, because suddenly you're golden, or one more method actually, type with fake method, and it's kind of nasty as well. Like imagine you start reflecting over your stuff, and boom, there's something you didn't expect. Like, is it public? Is it private? How do you deal with that? Like, not cool. And the last thing actually, that if we ever fix that, what we would do, we would probably use 0, kind of the overflow in the 2 bytes representation as that. But here's the thing: all the readers of metadata will be kind of confused by that, because nobody expects that. Like, there's like debuggers, there's profilers, there's IL spile, there's gazillion of things. I think Yaron, you had a metadata reader yourself as well, right? So imagine that's a problem in the whole ecosystem. If we fix that, if we go and fix the specification, or if we compensate for that certain way, we have to make sure that everyone would kind of do that, accommodate to that change, and it's just not worth it. So the lesson learned from is that sometimes, well, there are 3 lessons from me. One is that not all bugs have to be fixed, especially if they happen once in 17 years. The second thing is actually that fixing specification bugs is extremely hard, or it has impact on larger ecosystem. And number 3, that's kind of like my key takeaway, my personal takeaway, is that if you owned metadata and you didn't touch them for 7 years, people will come to you anyway after those 7 years asking question and like, can you help with this bug? So once you touch something, you're stuck with it forever, which is fun. All right, when we think about the specification bugs, one of the angle is basically it's kind of breaking change, right? You would have to do breaking change to specification. So that comes us to next thing, and that's kind of breaking changes in general. And it's funny that everyone who finds a bug somewhere, especially in our code or down underneath you, like you spend days tracking it down, you're happy, you want the bug fixed. Nobody comes like, oh, yeah, I found a bug, that's okay, you don't have to fix it, I'm fine, right? Nobody does that. Look at the GitHub, it's all the time. What's funny as well, that nobody wants to be broken by any change. And honestly, when you look at that, that's the one selfish point. Like, yeah, if it's in my way, please fix it, but please don't change anything else. It's extremely selfish. Unfortunately, those two things kind of don't work together. What's worse is that there's a realistic observation by actually Jan Kotas, our architect on runtime, a long time ago. He told me this, that actually 10% of fixes, even of his fixes, he's the super being, right? have unintended side effects. So something that is not anticipated in code review, nobody thought about that, nobody tested that, and it doesn't matter how many people you put on the code review, how smart. Just 10% of things have unintended side effects. Now the key question is the side effect gonna be, okay, some corner case somewhere, maybe we will find out once after 17 years, or is it something that, boom, you roll it out and it's gonna break people? So there's a risk always. And there was one extreme case that I lived through, which was mind-blowing, is actually when performance improvement broke application. We made something faster, and customer, well, we found out later, like, customer came like, oh, you roll out this, you broke me. Okay, let me look at that. And you dig and find out, I think it was the case that they relied on the order of type initialization or something, which you should never do, but guess what, nobody does it intentionally. Usually your code works, you're happy. One day, you deploy a new version of .NET Framework, your code doesn't work. Who do you blame? Yourself? Nobody does that. So you blame the guys underneath you, and you find out that actually, in that case, we actually speed up some things around type loading, and the order was something ended up faster, which means order was different, and instead of initialized values, they suddenly started getting the uninitialized value, which was perfectly fine by definition. But obviously, practically, it just broke them. What do you do in such cases? Well, you tell the customer, unless it's lots of customers and everyone is screaming at you, tell them like, sorry, it was a bug in your code, you gotta fix that. You depended on something unintentionally, but that you should not, tough luck, because otherwise, you couldn't change anything. If you cannot do even perf improvements, like, what do you do, right? It's a harsh life. The kind of lesson learned from that, or from these things, is that everything has, risk of breaking someone, everything. And I'm gonna have a couple of stories that actually demonstrate that very nicely. So this is a story from Windows 8 time, when there was on ARM, there was the push for the Surface RT, so big thing, and kind of like almost at the end of the, not almost, the end of the release, it was literally one last build or something like that. Finance team from, I think it was Bing Finance app or something like that, came to us that their app is suddenly started crashing. So you start digging. And you find out, that it was actually latent bug, so pre-existing bug, which was there for months, except in the last build, it got triggered. And it was funny that it got triggered because it had two conditions. The first one, you had to have a method in engine image, which is the, ahead of time compilation stored on disk, if you don't know that, not super important. But if you had that method, span across the 8 kilobytes page sizes, in combination with GC happening twice while you were at the call stack. And then this would trigger. So it's kind of like, obscure combo of things. Now imagine like, it happened only on ARM, so Windows RT, one of the key applications. Everyone is like, when is it gonna be fixed? What happened? How come you broke us? So it happened. What happened is actually that there was a really unrelated change somewhere else, entirely outside, that moved and aligned networking, actually default proxy, to be exactly on the 8 kilobyte boundary. And it's the default proxy probably kind of does some networking, so it takes a while, and startup of application is kind of resource intensive, and GC can happen multiple times, and boom, you hit this bug. So I bet that the people who who kind of triggered this somewhere down the path were saying, looking at the change, like, oh, this is absolutely safe. Like, instead of plus, we use minus. Nobody else uses it. Like, this is safe. Or maybe they added, one more call or something. Super safe change. The thing is that it pushed out the rest and triggered something somewhere else. So that's, extreme, example, but realistic. This is a real story, that anything, literally anything can break you. So whenever you see us on GitHub or on Framework, discussing with you, like, hey, I have a bug, like, fix it for me. Like, yeah, there's a risk. Like, what do you mean risk? It's simple. I see the fix. Like, yeah, it's a little bit more complicated. And this is one of the, it's a little bit more complicated things. Another angle how to look at breaking changes that I like is actually that some of them can have a really huge impact. And this is a story of actually real patch of .NET Framework, which is years ago. And there was certain text software, which I'm not gonna name, in US that got broken. And it got broken printing the text forms. That kind of sucks. Well, happened that the update was pushed a couple of days before the tax season. And that's not a thing you want to have on your resume or anywhere, right? Or in your portfolio. So that was a nasty thing. And that actually, obviously, the printing was broken. What's funny is that the scenario was recognized as important. It was tested by Microsoft. It was tested by the tax software company, except everyone tested printing to PDF file, because who the heck would print on printer in your test lab? And guess what broke? Only the printing on printer from some unknown reason. Tough luck. Imagine you're doing last-minute taxes, like I usually do, because I hate that thing. I procrastinate last minute, and then you cannot print it. Like, at least you can now e-file these days. I'm not sure. In Europe, it might be slightly different, but in US, that's how it works. Anyway, so that was funny. And the lesson learned is from this is actually you need to be extra cautious around some sensitive dates. And if you look at that, for example, like large, resellers and selling companies, online shops, they usually have this moratorium on changes around holidays, because from November to December they get 30%, 20% of all their income and whatnot. They don't push any changes. I have actually friends in those companies in Seattle that actually told me yep, I don't have to do anything now for 1 month. Even if I want fix, nope, then nothing gets through. I can now play, experiment and think, and then in January we're gonna restart again. So what's funny is that those things actually apply to something like .NET Framework, which you wouldn't naively guess that much. Well, yeah. Anyway, and now I'm gonna jump to my last story, which is actually a long one, and which is very interesting in my opinion. I love that one, even though I suffered a lot. And it's actually from last July. So July 2018, and even though it's from last July, it actually started a little bit earlier. It started January, so 2018 January, actually started in December, but we got looped in for the first time in January. And there was some researcher doing some kind of ML models and stuff, and using on Cosmos DB, and here and there, the results kind of didn't match what he expected. And it took him a while to, he bugged the team, the Cosmos DB. I think that back then they were not public yet, so it was kind of internal thing. And eventually they kind of came to us, I'm on networking team. That's what I was, networking team as well. And hey, something fishy is going on. We seem to we send some request and we get some nonsense back. It must be networking. And of course, .NET, where else, right? It took us a while, actually a couple of months, because first reaction to that, okay, so do you know if it's problem on client or on server? Because I own only the client side networking part. Yeah. Well, selfish. You need to kind of get the right experts in the room, right? It doesn't make sense to ask, I don't know, WinForms people what's happening in kernel. They will most likely not have the expertise. So anyway, the first thing, is it client side or server side? So they had to kind of deploy Wireshark, collect some traces, which in production is fun and non-trivial. Anyway, they managed to do that, and they actually there was enough proof that actually pointed hey, server is doing the right thing. It's kind of sending, receiving requests, sending the right responses. So something fishy is happening on the receiving side, on client side. Now, it still doesn't mean that it's .NET layer, but it's either .NET or underneath, or the application messing up something really badly, or the operating system. But who first is blamed? Obviously .NET, and it makes sense. Whoever's highest up in the stack should start an investigation. So we look at that, and that was about February time. And we got suspicious that there's some kind of buffer management that looks a little bit fishy. Let's find out who uses these buffers and how. So we added more logging, private build, and gave it to the team sometime in February. And in March we kind of knock on the door. So what's up? Do you have the new logs? And there's yeah, the repro is gone. It doesn't happen anymore. Okay, what happened? Well, we upgraded cluster, and suddenly nothing happens. All right, what do? You have no repro. You have no clue. You have suspicion that maybe buffers, or maybe it might have been some weird hardware bug or something. Well, probably not. Even to actually one part of the story I forgot to tell. Sometimes in the I'm sorry, I'm gonna jump between the stories. Sometimes actually in the hardware issues, you can blame even drivers. I have seen cases when actually drivers were causing memory corruptions and stuff, or antiviruses and that stuff. So sometimes we actually even have to ask does it run on different configuration. So this would be actually exactly the case when I would say hey, you guys have this cluster, maybe there was something fishy. So it works on new one, good. Well, it would be simple, right? It wouldn't be a long story, and the last one. So in May, we have similar reports coming, actually, report coming again. And what I didn't realize is actually there were two teams on the email thread because they were working already together. Somehow they found each other. They're parting on repro, saying like, "Oh, this is important. This is important." And we were like, "Hold on, like, is it server side problem, client side problems?" Anyway, before we kind of got too far, like, in 2 weeks, suddenly kind of blew out because it had some non-trivial impact on the fact that. Data have been mixed up, kind of in some larger services, and that ain't good. Let me put it this way. So there was like lots of kind of spotlight. So it was really all hands on deck situation, and there was an awesome thing. These folks, these teams, like came up with small repro. Like they basically did, kind of narrowed it down enough in their larger workloads. Figured it out, and had a small repro that was hitting Azure storage like crazy. And 1 in 20 minutes, actually, they hit this issue that they got wrong response to a request. And then they actually played with some, tweaked some kind of arguments of that, and it was like 2 pages of code. It was not really big. And they got it to 1 minute, which was, yay, we have a repro 1 minute, that's awesome. Now you can kind of start deploying your private bits, logs, and try to really investigate. What was even better is that they got time travel debugging trace. Used to be called IDNA or time travel tracing. Who knows what's IDNA or what's time travel debugging? All right, few people. For the rest, you are missing out on awesome thing. Of course, only if you do this, low-level hardcore stuff. Imagine that the time travel debugging is basically it records every single instruction what happens in the process, which means that if you have the trace, you can, it works only in DBG, sorry. If you have that trace, you can then say like, hey, something happened over here. You set breakpoints, data breakpoints, whatever conditional breakpoints, and then you say the beautiful thing, go back. And it executes it backwards and tells you like, oh, this is where the data was written. So you can kind of trace back what happened. Oftentimes in C++, when I used Fusion and that type of, it was lifesaver because there's 20 levels of if fail go. You have no idea when there's error at the end from an exception which path it did go because there's gazillion of passes reading that. So you just go back and say like, oh, this is where the error originated. Anyway, so we had this, and with that we were able to kind of debug and root cause the issue to actually HTTP pipelining under stress. Interestingly, it was 13 years, the bug was there for 13 years, since .NET 2.0. It was the first time second time, because in January it was first time. Second time somebody kind of hit that. I'm going to tell you a little bit about HTTP pipelining just for fun. It's kind of interesting. It's a perf feature. Who knows what HTTP pipelining is? All right, that's one person. Awesome. So classic HTTP is like you send request to server, and you get back response. Life is beautiful. Now imagine that you have multiple requests, you have multiple connections. You don't have like 10,000 connections. You have usually like 100 connections with the server. And if you're really under stress or on like heavy communication, think microservices and that type of stuff, right? You want to kind of request response. If you do it this way, the connection basically sends request and then gets response, and you're waiting on the ping there and back, and then you can send another request to get another response. So HTTP pipelining is about allowing you that you're gonna send multiple requests, and the server guarantees that it's gonna send answers, the responses in the same order. That's all, no magic, right? It's basically pipeline. So what you're gonna get? You're gonna get, for request, if request number 1 first comes and request 2, first you're gonna get response 1, and then you're gonna get response 2. Life is beautiful. Now, what if there are 3 requests? And what's more, what if some of them, that's in the area where the bug was, one of them is canceled? So because timeout or whatever, under stress, unfortunately happens, and this is stress bug. So if the request 1 is canceled, what do? You're waiting on the response 1, but you don't want to kind of wait on it. You basically say like, okay, this connection is done. We just cancel that. You're gonna have to retry the request 2 and request 3 somewhere else on another connection. Go away. Good. Life is beautiful. What happens if you cancel the last one, which is typical? Typical is the request 1 actually. The last one. If you do that, you just basically wait for response 1, then wait for response 2, and then you're done. You close the connection. Now, what if you cancel on timeout the middle one? which is kind of weird. Why didn't you, it's probably another shorter time than the request one, so the request one should be first, but if you're under heavy load, that can happen, and you need at least 3. Well, the code, what it did is something wrong, but it looked pretty innocent. It basically just removed that request from the queue. So you got the response 1, yay! You got the response 2 afterwards, and you use the response 2 for the request 3. Oops. So you send a request, and you get response from something else. What could go wrong? So imagine that the request was something like, hey, does this data exist? Yes. Oh, it did not. I got response from another request. Shoot. So data loss. Imagine, that was actually the case, you have a multi-tenant service, which means that there's multiple customers. And you say like, hey, give me data for this customer X. Oops, there's data for customer Y. That ain't good. So that was fun. So, some definition of fun, yes. It's gonna get better, don't worry. So, we had workaround, disable pipelining, which is perf impact, but obviously if you have to choose perf security, it's easy, right? Security wins. But in parallel, we work on the fix, we kind of figure out not to remove just the middle one, but basically cancel whatever is after, but it was sensitive code, so you have to, as I told you, like, you change code, like you want to kind of do the minimum fix, such that it fixes the thing and doesn't disrupt the rest, because it was ancient code base that nobody fully understood, and you don't want to touch it, you want to touch it as least as possible to minimize the risk, right? So we run the repro, and boom, after 4 hours with the fix, it fails again. Wow, you didn't see that coming. And has exactly the same symptoms. You send requests, and you get different response. To make it more interesting, the repro is sensitive to the times when you run it. So I was sitting, my family was already in Czech Republic last year, so I had easy time. So I could work like crazy, and it was fun. So whenever I worked and finally got out of the management and discussions into the coding, I couldn't repro it. I was like, what am I doing wrong? Am I dumb, manager? Probably yes. But turned out actually I was less likely to reproduce it after hours. That didn't help. What was even worse, that we were actually not able to debug it, so to catch it under IDNA, time travel debugging, that's the new word, that's the new name, which kind of sucked. We tried, because that would, again, we would just go back and figure out. It's just, as soon as we have time travel trace, the debugger, time travel debugging, you know that you're gonna find out what's going on. It's just gonna take time, that's all. But you have all the information available. No. So with this, we started again suspicion, has suspicion about the buffers, what started originally. So we reused the old bits, and of course, we found bad lifetime management on the sending side. So we sent a request, and before it went out, the buffer was reused, and another request came and used the same buffer, and now this request was sent with the content of the other request. So boom, you basically suddenly sending twice the same, same requests twice, and sometimes even to different servers. Oopsie, that's not good. Turns out to be 5 years old bug, so only 5 years, in 4.5.2, and with very similar symptoms, right? Karma is karma. Turns out that that bug was introduced when, on my team as Perfleet when we made perf improvements to networking, which I know now. So I kind of introduced myself this fun bug, kinda indirectly. Anyway. So we were looking for, like, before, we knew how to fix it and everything. Or it was complicated as hell as well. But we tried to kind of find out, like, what triggered this. Why now? Why suddenly out of the blue? And luckily it was a Skype team, and they were awesome. If you know the feeling, the saying, like, I do not test, and if I do it in production. So this was it. In these things, like, sometimes you need it, because, small repros don't always work. And they were able to basically, on 24 hours, put out patches, try out en masse, because for them, the failures that they've seen, they had retries, so they kind of compensated. So customers were not hurt, so we could easily experiment. Like, awesome. When you have customer like that, or partner like that, or you're golden, and that's beautiful. It almost never happens. Anyway, with their help, we were able to trace it down to actually change in .NET for 7.1 that there was a fix. What was funny that fix was exactly around the place where the bug was. So imagine like this, like, there was a function, and at the bottom, originally, we released, returned the buffer, and reuse the buffer. And instead of that, the fix in 4.4.7.1 was like, let's do it a little bit earlier, which means, anyway, like we kind of decreased the number or the time frame when it could happen. And that triggered the bug. The right fix was actually to move it even higher up. Why? Actually, that's not it. It's very counterintuitive. Like, we look at that as like, this should have helped. This should not make it worse. Yet it somehow magically triggered the stuff. So go figure. And then we did code review, and we found out similar bug on the actually receiving side of the same code. Again, lifetime management of buffers was incorrect. But this was different code. It was different type of bug. Kind of similar area introduced in the same change 5 years ago. So that was fun. And what was mind-blowing, that basically, why so many customers and services suddenly out of the blue hit the same issues at once, right? There's silence. One bug, 13 years old. Like, another 5 years old. Actually, triggered recently. So maybe the upgrade helped. I think that Skype was the team that actually upgraded 2.4.7.1, and that's why they said, oh, this broke. This kind of started hitting. So that's why we narrowed it down for them. But the other services didn't. When we thought about it, the only thing that we could blame was probably some Spectre and Meltdown fixes that went into the OS like few months before that. So by that time, they were being rolled out everywhere. It might have changed timings and things, and that might have triggered the ancient 13 years old thing. And honestly, maybe it was just magic. We don't know. And we tried hard, pretty hard. We invested like weeks into trying to figure out what might have been, why now? And Scott did some kind of investigations and things, and we didn't get really far. So the lesson learned from this is that weird coincidences happen, like multiple bugs narrowing down on you at the same time without any reason. Yeah, it happens. Lessons learned, I'm gonna do just short recap. What we talked about is lesson number one that we learned over here, or I want to tell you, is that, always ask, does it repro on one machine? If you see it on GitHub from me or somebody else, don't be offended. We're not trying to make your life easier. We're protecting ourselves from the costly investigations, because they are freaking costly. Some bugs happens only 1 in 17 years, and maybe it's okay to leave them there, Not everything has to be fixed. Spec bugs are extremely hard to fix. That was the metadata for Modbug. Then really anything has risk of breaking change. There was actually extreme case. There was the story about innocent changes can kind of push the sizes, expose latent bugs somewhere else. It was the 8 kilobyte push. And the impact may be huge, like, for example, for the text software. Actually, a colleague of mine, my boss now from MS Build, he actually told me the story that he saw, I don't know exactly the details, but he saw a bug when actually rebuilt, just rebuilding the product. No change, just rebuild, triggered existing bug. Which is that's mind-blowing, right? When you have that, you're just scared to even touch the keyboard, right? Which we are all the time, right? Anyway, one key takeaway, if I want you to come out of this something, always try to create small repro. That's freaking amazing. Once you have that on our level, on your level, it's super easy to debug. It's super easy. Oh, super easy. It's much easier to debug things, and it actually makes it possible. Customers, especially on GitHub, often say "Oh, I have a bug. It's your problem." Okay, give me repro. Oh, I cannot give you. It's the end-to-end large thing. Is I'm not debugging that. Well, I'm not creating small repro. Well, you should. Well, that will take my time. What do you think the debugging of your end-to-end will kind of cost us, right? So that's kind of when we asking for small repros, and that's when actually you get better return as well from .NET teams and from any teams. Imagine your software. If someone comes to you you have a bug, and that's it. There are reports like that. It's no kidding. Yeah. What do you do about that, right? Or even here's the call stack. Or, well, that's the better, here's the error message, null reference exception. Thank you, that's helpful. Now I know where to look, right? It's not actionable. As soon as if someone goes down and tells you hey, if I do this, at least if you have steps or you have something small, you are more willing to come jump on it, investigate, go farther, go above and beyond, and help the person. So same from our side. It just makes life easier. The time travel debugging, if you ever hit anything around that, like look into that. It's freaking amazing. It's WinDBG, so you gotta learn a lot. On the other hand, it's powerful, extremely powerful, lifesaver several times. And one key takeaway, sometimes there's just magic. Alrighty. I would like to thank you. If you have feedback on this talk, not only positive, but I'm looking for constructive feedback, something that was not funny enough or too much funny, slow, too fast, whatever, boring, please tell me that. There's a tweet actually during NDC, I asked the same and hinted that actually most speakers, if not all, want feedback from people because that's how we get better. That's how we can kind of find out what's better or not. If somebody just tells you like, oh, that's great, okay, I did probably a good job, but if you can come up with something, hey, I would love this to be better, it's awesome. Use it as well for the speakers. This is Steve, he's gonna talk here as well. So, thank you. 45 minutes, awesome.